All right. So a couple of different examples here of functions that you've seen before. If you could sketch the graph of f of x equals 1 over x. And then also sketch the graph of g of x equals x squared. And let's talk about continuity in two. So the graph of 1 over x, do you remember what that looks like? Where is its vertical asymptote? Where are its two branches? What quadrants are its branches in? First and third, yeah. Vertical asymptote at x equals 0. So 1 over x is discontinuous at one place in the domain of all real numbers. It's discontinuous at x equals 0, right? It's got a vertical asymptote there. So we call that a point of discontinuity. We call that a vertical discontinuity or something along those lines. Whereas the graph of g of x equals x squared, if you think about the graph of that, it's continuous everywhere over the real numbers, right? There's no place where it is not defined on the real numbers for g of x equals x squared. So we've seen discontinuous functions. We've worked with them. What's interesting about f of x equals 1 over x is it's really continuous everywhere but at x equals 0. I mean, it's pretty predictable. It's continuous. It's a nice function everywhere except at that one point where we have a vertical asymptote. So what do you think continuity means, like in your own words? What did you come up with as you were going through that activity yesterday, the limits and continuity? How would you define continuity at a point? Do you remember? We had a few different things that needed to happen. We were looking at those graphs and their limits. I think I called them 3 pillars. Remember one of the 3 pillars?
Or every point of the limit, or
yeah, so that would be cover 2 of the pillars. Yep, the left and right limits have to be equal to each other, and then they have to be equal to what? The value of the function at that point. And that's really the formal definition. But that is the definition of a limit. It means that, and we could write it down now, because we have that experience with going through that Desmos activity, we know that the left and right limits have to be equal, or the limit must exist. We could just say that. That includes left and right limits are equal. So the limit must exist. Must exist. And this is continuity really at a point, okay? So the limit must exist at the point, and the value of the function must equal the limit. And that really is the definition of continuity. That's better than what we would have expected in your own words, but we had that activity yesterday. So that is continuity at a point. Okay, so this is the definition of continuity at a specific point. And so if you think about those examples of, like the example f of x equals 1 over x. There's a branch here, there's another one over here. It really only fails to be continuous at one single point, x equals 0, right? It only fails to be continuous at that one point, x equals 0. Otherwise, we could say it's continuous every other place. And so in terms of continuity of a function, that would just mean that it is continuous at every point in whatever domain or interval you give it. So you could essentially say that 1 over x is continuous on its domain, right? Everywhere but at x equals 0, it's continuous. But over the entire domain of real numbers, it is not a continuous function. So for that reason, we would refer to it as not being a continuous function because it's not continuous at every point of C in the real numbers. And we would say that the type of discontinuity it has is a vertical asymptote, is what we've said. And so there are some different types of discontinuities we've seen. One of them is a vertical asymptote. We'll talk about the others in a little bit. That is the definition of continuity. The limit must exist at the point, and the value of the function must equal the limit at a specific point. All right. So here's an example here. Okay, this is our greatest integer function. You remember, do you think you could sketch this without drawing it on your calculator or do it on your calculator first? Do you remember? The int x function, this is incredibly discontinuous over the real number. It is. Do you remember where the first step? So from the origin up to 1, 0, we've got a little line segment, right? And then we've got an open circle at the right end of each line segment. You remember that? So looks like this. So we got closed circle here, open circle there, and then it jumps up here to 1, 1, has a closed circle there, open circle on the end, and then jumps up to 2, open circle there, and it keeps on going, closed circle here, open circle here, and then back here, closed circle here, open circle there. So what it's doing is, if I plug in any value between, say, 0 and up to, but not including the x value 1, it will spit out 0. Or if I go and plug in any value between 1, including 1, and up to, but not including 2, it will spit out 1. Okay, so it truncates it, really, it cuts off everything past the decimal. Okay. And so it's terribly discontinuous. So what makes this not continuous is the idea. So the first one we saw, the 1 over x, was a vertical discontinuity. It was a vertical asymptote that made this kind of discontinuous. What about here? What's happening? How would you describe the discontinuity here? Have any words to describe it? Awful. Awful. It's awfully discontinuous. It's a great function.
Yeah, the directional limits disagree.
Yeah, the directional limits disagree. Yeah, you could write that down. Directional limits or one-sided limits disagree. And we have a specific name for this. We're going to call this a jump discontinuity. So we call this a jump discontinuity. It jumps. It's like if you were running along here, you'd have to run, jump, so the jump discontinuity. The vertical asymptote, man, you'd run up to that one and try to jump and never reach it. Just fall in the abyss. But there's a vertical asymptote. We've got the jump discontinuity. The one-sided limits disagree. So there's two different types of discontinuities. So in this section, they're going to ask you types of discontinuities. I'm fine with vertical asymptote and jump. Okay. So the informal, what's going to be on the description? Same thing. Jump. Yeah, you could use the same thing. But you should understand why we have a jump here. Why we the discontinuity is that the one-sided limits don't agree. We disagree. That whole series of questions, kind of like what I asked you on the last question on the quiz, that type of thing is where left-hand limit is one thing, right-hand limit is another thing, so therefore the limit of none is jump. Or the one where we have the hole there, where the limit does exist, the one-sided limits exist, but the value of the function is not defined. So that's what we call a removable discontinuity, and that we've seen already. So the hole is the removable discontinuity, and that's the third type. And then they sometimes throw in a fourth type, and that's oscillating. It just oscillates too much, so oscillating discontinuity or oscillation. But the standard three are vertical asymptote, jump, and then the whole, or removable discontinuity is what they call it. It's removable discontinuity. All right, so definition of continuity. To be continuous, we say a function is continuous if it is continuous on every point of a specific interval or domain. Put interval in here. And a lot of times in calculus is we will pick the interval. Like it might be continuous, like 1 over x is continuous from open interval 0 up to infinity, but it's not continuous over all real numbers. So just pay attention to what the interval is. But in general, if they just ask, is the function continuous, you're assuming over the entire set of real numbers and then stating it's not because of the verb class. But pay attention to the interval. Typically, we define continuity as pointwise continuity at a point. And pointwise continuity is the limit exists, and the value of the function at that point is equal to the value of the limit, meaning the point by point. All right. So how would you verify that a simple quadratic equation like f of x equals x squared is continuous at x equals 2? What would that verification look like? Okay, find the limit at 2, so we'd write limit as x approaches 2 of x squared equals, we just find it equals 4, and f of 2 equals 4. Then we'd make a statement since the limit exists. Limit as x approaches 2 of f of x exists, and limit as x approaches 2 of f of x equals f of 2. F of x is continuous at x equals 2. And this function we know to be continuous over the entire interval to real numbers, right? But that's what you would have to do to prove that it's continuous at that one point. And usually we're just evaluating these functions a lot of times at one point. So like if they throw up a greatest integer function, they're going to ask for the limit as x approaches a specific value. And it's probably going to be one of those problem points. Okay, one of the places where there's a jump, and you'd say it's discontinuous because the one-side limits are different, so therefore the limit does not exist. Or for the verb class asymptote one, the point in question would be the verb class asymptote. So you'd say the limit, or the function is not continuous because at x equals 0, say for example, the function is not even defined. So you could kind of argue that in different ways. You could say the limit doesn't exist and there's no way it could equal the value of the function because it's not even defined there. That's it. So, you know, this type of write-up is the type of thing that we're looking for, is being able to use the definitions to demonstrate continuity at a point. And it's not that complicated. It really isn't too hard to do. All right. So some different discontinuities here. We have 3 types. Do you remember what they were? If you haven't written these down already. So we've got, the first one was vertical asymptote. Second one was jump. And then the third one I just mentioned in passing, but it's a removable discontinuity. discontinuity or hole. Yeah. You could use the word hole, and that would be fine. You might want to reference removable discontinuity if you're actually factoring out something and canceling it. Type of thing. Like what happened in the quiz. Factor out. So here's our example of the third type. Okay, so what type of discontinuity does x minus 3 over x squared minus 9 have at x equals 3? I don't know. Let's see. You got to factor first. So factor it first. So go ahead and write down this function. We'll do it together. So f of x equals x minus 3 over x squared minus 9. So we have one of these categories. So we've got x minus 3 on the top. A little bit of factoring here. X minus 3, x plus 3. And so my function f of x ends up being 1 over x plus 3. 1 over x plus 3. So what type of discontinuity do I have at x equals 3? Removable. It's a hole. And then at x equals negative 3, we have a vertical asymptote. And so those are two of the three types there on that one function. So it does as a whole. Like if you go to graph that, it's going to look like 1 over x. It's going to look like 1 over x, shifted 3 units left. It looks kind of like 1 over x. But at 3, if you were to plug in 3 here, it would be 1 over 6. So at 3, comma 1/6, we have a hole. I might even just draw it here. This is something we did last year. Let's go ahead and draw this thing. So, whoops. Let's try it again. Here, we'll draw it up. So 1 over x plus 3 would be shifted 1, 2, 3 units to the left. We have a vertical asymptote right there. And at 3 comma 6, what did I say? 3 comma 1/6? Is that what it was? 3 comma 1/6. Yeah, if I plug in 3 right here, it would be 1/6. So 3 comma 1/6, we have a hole. So 1, 2, 3 comma 1/6. Right about here with a hole. So there's a branch that goes there to the hole and keeps going. And then there's another branch over here to the left of the vertical asymptote. So both discontinuities as you go from negative infinity to infinity are shown there. The vertical asymptote and then the hole. All right. Here's a step on this. Let's do this first, then I'll do an example. So to remove a discontinuity, here it is. Find the domain restriction. Find domain restrictions. Factor and divide out common factors, and then rationalize out the offending terms. So that's what you've been doing. We say find domain restrictions because if you look at the domain restrictions, like what makes the bottom undefined, if that's not even within the domain that we care about, then you don't need to worry about it. But you factor and divide out common factors, and then rationalize out the offending terms. So you're going to be asked to take some functions, kind of like you did in the activity the other day, and find out a way to make them, like put a hole or put a point back into that hole, to define the function piecewise in such a way that you can then make it continuous. like we're going to do right here. So go ahead and write down this function. It says let f of x equal x squared minus 3x plus 2 over x squared minus 4x plus 3. And then the last one on there is a k, and we're going to find that value k that will fill in the hole at x equals 1. So we're going to take this piecewise function, which has a, I'm assuming, removable discontinuity is what we got to do. And what we're going to do is fill it in. Because if you think about it, if I have a vertical asymptote, I'm not going to be able to make it continuous. Like there's no way I'm going to define it in such a way that's going to make it continuous. And then I think we saw this in the activity yesterday. The jump discontinuity would require us to take the two pieces, the two one-sided limits, the two segments, I think is what they had you do, and bring them together. And one of the ends would have to be a filled-in hole. And then the removable is just a matter of defining a specific y value to go with x equals 1 in this case that will fill in the hole. That's it. So it's a specific y value that will fill in the hole. Super easy. When we say rationalize out the offending term, all we're going to do is get our simplified version of this function, plug in 1, and whatever output we get when we plug in 1 to the simplified out version of this, the rationalized one, is the value that we're going to make k to fill in the hole. So go ahead and factor the top and the bottom. What do you get when you factor the top? All right, x squared minus 3x plus 2, x minus 1, x plus 2, and then the bottom one, minus 1, x minus 3. Okay, so that simplifies into x minus 2 over x minus 3. And then all that you have to do is find what f of 1 is of that simplified or rationalized, that simplified rational expression. So if you can find f of 1, or really I should call it probably g of 1, because this is a new function that's simplified. But f of 1 is equal to 1 minus 2 over 1 minus 3. It's parentheses around it. Or negative 2 over, or negative 1 over negative 2, so 1/2. And so I just need to define k equal to 1/2, and that will fill in the hole. That will fill in the hole. And we should say to make f of x continuous at x equals 1, because we can't make it continuous at x equals 3. Okay? So at k equals 1/2, if you just put in a 1/2 here, and that's literally what we'll do, is we'll just add in f of x equals 1/2 when x equals 1. So if I go to graph this, I'm going to have a rational function. It has, oh, by the way, what's the horizontal asymptote in this guy? 1. Yeah, so I have a horizontal asymptote at 1. I have a vertical asymptote at 3. I've got a couple of branches there. And I've got a hole at 1, 1/2. And I just filled it in by saying when x equals exactly 1, just make it be, the function be 1/2. So all that you have to do to make a function that is not continuous because of a hole continuous is simplify it and plug in the value at which it's undefined. And then that label that y value as part of your piecewise function. So I'm going to ask you to do that in the assignment as well. All right. Why don't you try this one? See if you can do this one on your own.
What's up, Dave?
How's it going? What's up? Back on. Okay, you should have gotten W equals 32. You have to rationalize the denominator here by multiplying top and bottom by root x plus 2. So W equals 32. So you just put a 32 in there in place of W. So that fills in that one hole. Okay? And this one doesn't have any vertical offset. All right. W. Okay, so here's what we've done so far. 3 types of discontinuities. What are they? Vertical asymptote is one. Hole is one. We call it a removable discontinuity. I'm going to jump. And then the only other thing I've shown you so far is how do you fill in the hole?
With dirt.
It's simple. With dirt. That's great. We'll get you right on that. So to fill in the hole, you simplify it and then plug in the point in question. The point in question is always going to be this stuff over here. Good. That's kind of that giveaway. And then whatever you get, you plug this into a simplified version of this. We'll fill in the hole. Okay. So we're going to change gears a little bit here. This is the first of our big theorems. We have some special theorems. They're super special if we start to abbreviate them. And this is one of the abbreviated ones. We abbreviated IVT, or intermediate value theorem is IVT. It's a big theorem. You need to write it down, and then I'll try and explain it here. But a theorem, and this is kind of my shortened version of it. I'm leaving out some of the conjunctions in between, but on the left of the arrow here are the given parts of this theorem. Going back to geometry, right, there's always some givens, and then there's some conclusion here, or conclusions. So the given parts is if f is continuous on closed interval AB, m is an element of the real numbers, is what that's saying, and m is between f of a and f of b. All those things must be true for the intermediate value theorem to be applied. So I'll let you write those down. So f is continuous on AB, and you do have to memorize this. So that's why I put it in this form. I think it's easier to memorize in this form rather than the paragraph form that they give you in the textbook. So f is continuous on AB, and that's going to be like part of the given for each of our 3 big theorems in here, okay, leading up to the fundamental theorem of calculus. So f is continuous on, in this case, it's a closed interval AB. It doesn't always have to be a closed interval. But for the intermediate value theorem, it has to be f is continuous on a closed interval AB. M is an element of the real numbers. So m has to be an element of the real numbers. And then m is between f of a and f of b, not necessarily including those values. Then, that's what the arrow is. Then there exists a number C, well, it's a letter there, but some number C is representing a number, in that closed interval from A to B, where f of c equals m. Yeah.
What do you mean when you say f is an element?
Just m is a real number. It's not a complex. It's not. It doesn't have an I attached. That's why. Then there exists a C in AB where f of c equals m. Sounds more complicated than it really is. I'll show you it by picture here. I'll show you by picture, and then we're gonna find that value c for a certain function, a quadratic function, which we've done before. But this is just an existence theorem. It says something exists, but not necessarily where. Sometimes you can find where it is, but not always. Sometimes you just can't do the algebra to find where it is. It'd be like some of the, you might have some function that you just can't solve it. You can't find the zeros. You can't find, or the intersection with a specific value. So here's a nice continuous function. See here in black, guys? We have a nice continuous function on a closed interval between a and b here. So maybe draw a nice continuous function like this one on a closed interval from a to b. And you have some value m right here that is below f of a and above f of b. In other words, it's between f of a and f of b. It's between, and we say strictly between up here. So it can't be f of a or f of b. That could be problematic. But it's got to be between f of a and f of b. Then there is some value c between a and b. So some value, you can plug it into the function, and it will be equal to that value m. This is the idea of continuity. It's just saying that you pick any two y values for a continuous function. Okay? Any two y values where one is strictly above the other, okay? Then there exists an x value that when you plug it into the function will give you some number between those two y values. That's all that it's saying. It's just saying there exists some output in between those two. And yeah, there has to be if it's continuous. I'll show you what I mean with this specific function. It's my next example. But this is the intermediate value theorem. So with continuous functions only, so if you have a hole or a jump or a vertical asymptote in there, then you could actually pick the one point in there that it won't have something to match up with it. But if it's a continuous function, and you have some y value in between f of a and f of b, then there will be an x value that when you plug it into the function will give you that specific y value. So let's find a nice, easy function to do this with. We're going to apply the IVT. Here it is already. We've already become friends with it. Labeled it with 3 capital letters. It's important. The IVT, if possible, on 0 to 5, so that f of c equals 11 for the function f of x equals x squared plus x minus 1. So we're going to apply the IVT, if we can, on the closed interval from 0 to 5, so that f of c equals 11 for the function. So let you write that down. There's a specific function, then we'll go ahead and do it. Intermediate value theorem.
What are we trying to do?
The intermediate value theorem is just saying that here's a parabola, right, on a closed interval 0 to 5. If I pick some number 11, I'll show you just a minute. This number 11 we're going to find is between f of 0 and f of 5. So we got to first find f of 0 and f of 5. Demonstrate that 11 is between those two numbers. And if that's true, then it's, because it's continuous, there exists some number between 0 and 5 that I can plug in here that will equal 11. That's what it's saying. That's going to be really important as we move into the idea of a derivative. So, okay, there are three parts to the given for the intermediate value theorem, and all of those have to be met. This is a big idea on the AP exam. Is of these 3 theorems we're going to focus on this year. There's 3 of them, big ones. You've got to make sure that the conditions are met and write that out in some mathematical and grammatical way so they understand it. So one of the first one was that we had to be on a closed interval, right? So we've got f is continuous on a closed interval. Would you agree that this is continuous, just based on your knowledge of functions? It's a parabola. Are there any problems with parabolas? No. So, and that's good enough for that. So since, let's go ahead and write all this down here. Since f is continuous, we'll abbreviate here, on 0, 5, what was the second thing now here? So it has to be continuous on a closed interval. The second thing was that n has to be a real number. 11 is an element of the real numbers. Okay. 11 is a real number. Doesn't have an I attached. And there's another part here. We have to demonstrate that 11 is between f of a and f of b. What is a up here? A is 0. And b is 5. And m is 11. So let's do a quick calculation off to the side here. Or up here maybe. F of 0 equals what? Plug 0 in here, you get -1. And f of 5 equals, a little harder, 25 plus 5, 30 minus 1, 29. So, and, so here's what we have. You could even write it out, f of 0 equals -1. Rather than just writing f of 0, but f of 0 equal to -1. 11 is between that and f of 5 equal to 29. You could, they would accept it. You could just say f of 0 and f of 5. They might ask you to show, actually I think they would want you to show -1 and 29 specifically because 11 is clearly between those two. But if you did the calculation, just wrote -1 and 29 here, that would be fine. Then there exists, okay, there exists a C in 0, 5, and if you go back here, it's so there exists, if you want to use that symbolism, that's fine, a C element of 0, 5, so that's how we're writing it out, same way. And then such that, there's a symbol for such that too, it's a backward D, but we'll write out such that f of C equals 11. So there exists one, and in this case, we can actually find it. So we're going to apply the theorem. So everything was met, all the conditions were met, and so here's what it looks like. We're going to just set 11 equal to this function with C plugged in, so C squared plus C minus 1. If I can solve that for C, I can find the specific value of C. If I went to write 11 equals, plug in C to the function, I can't algebraically solve it, then we know it exists, but we don't know what it is. What'd you get? So we got 0 here equals C squared plus C minus 12. We go ahead and factor. 0 equals C plus 4, C minus 3. Set each factor equal to 0. So we get C equals -4 or C equals 3. Well, give us some insight here, Aiden. You said only 3. Why not both of them? Yes, -4 is not in the interval from 0 to 5, right? So we're only looking for the one value that is in the interval from 0 to 5. So C equals 3. I should write this in this color. So f of 3 equals 11. So we not only showed that it existed, but found what it was. And we could do that because it was a quadratic function that we could solve by factoring in the quadratic format. Okay. If I had, say, a polynomial function that was not factorable and was higher than second degree, I could say a C exists, but I might not be able to find it. Okay. Well, I could with the calculator. With technology, at least to a certain point. Right? Technology, yes. All right, so that's it. That's the intermediate value theorem. I'm going to ask you to do this too on the second for a function that you can do. So it amounts to just taking the number they give you, the y value, and setting it equal to the function with c or x plugged in. Don't pack up yet. There's more. I wanted to do this with a slightly more complicated. In the textbook, you'll notice that sometimes the problems are a little harder, but that first example that we did was pretty simple, filling in the hole. There's something like this in the textbook. I think we'll end with, yeah, we did one like that already. We're going to end with this one right here. It says find a and b so that f of x is everywhere continuous. Okay, and this one's a little more complicated. Go ahead and write this down, please. It's going to take you longer to write it down, though, than it will to set it up and solve it. I think it or just as long to write down the problem. It's really not that bad if you understand what it means to be continuous. It's really not that bad. So we got f of x equals 1/8 ax cubed minus bx plus 3. So we've got this cubic, got this parabola, and we've got another cubic here. And I'm gonna show you visually what we're doing here, just so you have an idea of it. Like throwing the a's and b's in there takes the calculator out of the mix. You can play around with it a little bit, but I'll show you kind of what we're doing. We have a cubic. This is actually a cubic to the right. Let's just draw a generic cubic somewhere up here to the right. Okay. Generic cubic. We have a cubic to the left of 2. Generic cubic. And what we are trying to do is, and it can be done, okay, using just some basic algebra, is we're trying to take this cubic, move it into right there, and take this cubic, move it into right there to make it all continuous. That's what we're doing. See, this is just an equation that gives you 1 point. Yeah, it's a quadratic, it's a parabola, but who cares about the rest of the parabola? This is an equation that gives you 1 point, and you can figure out what this 1 point is. This 1 point is whatever you get when you plug in 2 here. What do you get when you plug in 2 here? I think it's 2, if I did my math right. Did you get the same thing I did? Okay, so this is just 2. So I know that I've got to make all 3 of these, when x equals 2, equal a y value of 2. It's kind of confusing. I remember this before. I wish it were something other than 2. But the y value has to be 2, and that has nothing to do with the x value. That's just what we're getting when we plug the x value of 2 into this equation. You with me? So what this amounts to, it's really simple, is a system of equations. It's really a system of equations that looks like this. 1/8 a times 2 cubed minus b times 2 plus 3 has to equal what? 2. And which 2 are we talking about? The x equals 2 or the y equals 1? Yes, and that's I'm sorry, but that's, I took this from the textbook, or I took it from somewhere, and it worked out that way. I go, oh, that's too bad. That was unfortunate. And then this guy right here has to also equal 2, okay? And all of that is based on what I get when I plug in 2 there. It's kind of like, here's the y coordinate, it must all meet up at to be continuous. And that's it. That's it. So this is about, there is one like this on there. So you would have to solve for a and b, and you've got all kinds of methods. I mean, you could use substitution, you can use elimination, you could use the intercept function on your calculator, you could use matrices, right? if I threw a third letter in there, you might want to use matrix algebra. Okay, so
That was a while ago.
I know.
Yeah.
So are you guys okay for finding A and B?
Yeah.
So you find A and B, whatever method you want to use. I would probably just use elimination. Yeah.
The elimination seems like the easiest, like, ways, like, no matter.